Thank you. And that's a mouthful. I'd like to start with a small anecdote. Like mentioned in the introduction, I was a customer for a long time, and then an opportunity turned up to actually join Ciena. And people were telling me, Freek, what are you doing? You're joining the dark side. And I was like, oh, what did I do? And no, I don't regret it at all. Here I am 9 years later. And I'll give you an update on what we do as a Ciena, so coherent developments in this particular region. Brief introduction of Ciena as a company. Some of you might know us, some of you might not. So we develop solutions for the fiber optic transport in the WAN area, wide area network. So lots of fiber optic terms in this talk, but I'll take you gently, if that's okay. We are globally, operating globally, let's say global customer base, 8,500 employees, of which just shy of half involved in R&D. So we take a certain level of pride in being a quite vertically integrated systems developer, let's say. We do, and in terms of systems, we do hardware, software, and services around that as well. We're, at least for the last fiscal 24, we were a $4 billion company. And we operate, in terms of the WAN, we operate in every sub-arena of the WAN. The submarine, so tens of thousands of kilometers in regional and long haul. Then the metro being, let's say, 100 or a few hundreds of kilometers at the edge of the network. So actually reaching, for instance, a cell site or a small business site. And there is optical all over there across that whole spectrum. Taking a step back, let's say, from and having a look at the current situation out there in the optical transmission, well, almost ecosystem, one could argue. So what's happening over there? Well, in a sense, one could say there's not a lot happening, but what is happening is huge. So if for up to a few years, networks were mainly centered about individuals interacting with a cloud at some point and with a network in between, since a couple of years, cloud to cloud has become actually a total pillar of its own in terms of network solutions. And it's driven by, you almost might have guessed it, AI. So AI has really emancipated, let's say, cloud-to-cloud connectivity as opposed to just user-to-cloud. So both are now two distinct columns. And what's happening in the cloud provider market is massive data center interconnect. And I'm not talking data center like a data center of an insurance company or something like this, but I'm talking huge data centers, and they need to be connected together. And it's all driven by, let's say, even generative AI. Terms like training LLMs, inference traffic or usage traffic generated by AI, hyperparameter settings, ingestion. So all these terms originate from the AI line of activity, and they're driving developments at the moment in network infrastructure like crazy. How does that reflect to this region? Well, actually quite good. And there are several reasons that we recognize why this is such a good match. So data centers, why does it match? Well, there is something to do with warmth, right? So data centers, there is lots of lots of compute happening. That warmth needs to go somewhere. And in a relatively low temperature climate, that can be done efficiently. So climate is an opportunity. there is, for instance, especially in Norway at least, there's the hydro. So in terms of renewable and available energy, there is a tick in the box as well for large data centers. I was almost saying the political stability, but it's also a stable, let's say, environment from geographical point of view, right? So all these things look favorably onto the investment scenarios, let's say. Connectivity is especially well provided as well. So lots of AI traffic is east-west, albeit with the UK in between there maybe. Lots of fiber optic cables across the North Sea and in the Baltic Sea. And like one of the previous speakers mentioned, there are plans to even go via North Pole route for 2 major infrastructure projects, thereby building, let's say, a redundancy for lots of subsea cables that currently traverse the Red Sea area. So these data centers, are they then being built? Yes. Finland is attracting lots of investments from Microsoft and Google. Brookfield invested in Sweden for up to USD 10 billion, which is significant. And the one that took yours truly by surprise, actually, was the recent announcement of Stargate Norway in Narvik. So that's a data center location to house 100,000, not in the first week, but up to 100,000 GPUs, graphical processing units, to provide AI compute. So massive movements over there. But then what does it mean? What do we have to build then in this fiber optic WAN of yours, Freek? Now let's start out with the basics. We have 100 gigi point-to-point service probably needed. Maybe a 400 gigi. So what do I mean? Well, 100 gigi from A to Z with a couple of 100 kilometers of fiber optic network in between. Maybe a 400 gigi. Probably will go to 800 gigi in the near future. So 1 or 2 of those circuits, Freek? No, probably you'll need a handful or even more. So at least it would be a stack of transponders that each provide, let's say, a 400 gigi point-to-point transparent service over an OLS, optical line system, covering hundreds of kilometers or thousands if that works. And another model is popping up where we see that the companies behind these data centers, they say, look, I don't have this network. So they call up a regional service provider who does have a network and the local manpower to look after it. And they will just expedite the whole network infrastructure, the fiber optic infrastructure, to that regional service provider. So they will pose some requirements, so much capacity between A and B, again, with WDM in between, across 1,000 kilometers, let's say. Here you go, regional service provider, build me this network. It needs to be vendor A by ABC. And that's what we call a MOFN, or Managed Optical Fiber Network. So the companies behind the data centers expedite the whole network industry, the whole network aspect, to a regional service provider. Another model which is more looked into than actually deployed, I have to admit, is something called spectrum leasing, which is totally happening at just the photonic level. So thereby one can, let's say, technically split up the available spectrum in a fiber optic strand between 2 different customers. So what's got Coherent to do with all of this? So what is Coherent, in fact? The shortest of introductions, if you please. So the top half of this diagram shows something called intensity modulated direct detect. What does this mean? It means that The transmitter of a device sends out, by means of a laser pulse, signals to a receiver at the other end of a fiber strand. And the only thing that the receiver will do is check, do I have an incoming pulse of light, yes or no? If there is some light coming in, the receiver will decide, okay, that's a 1 in the bit stream. If there's no light, it's a 0. Excellent solution for low data rates, for short distances, for instance, inside a data center, a 10 gig pluggable optic, for instance, SFP+, yeah, you're going to make that as simple as possible. But all these more massive solutions I was talking about just ago, they require something else altogether. They require the combination of both high data rates, but also large distances, hundreds of kilometers. And that's not going to work with just this receiver that will look, oh, I have a pulse coming in, and that's a 1. I have a 0, I have no pulse, that's a 0 in the bit stream. And there we have the coherent transmission technology coming in. It involves much more than just this intensity. So it involves, indeed, it does involve amplitude, but it involves phase and polarity, for instance, as well. And one gets to do with constellation diagrams like this, and those constitute, let's say, a transmission signal across a medium. Technical term for this one would be 16 QAM. There's 16 points in this quadrature amplitude modulation scheme, and each point in this constellation denotes a series of zeros and ones, let's say as encoded. So over time, the transmitter, using those, let's say, for simplicity, those 3 properties of light instead of just the single amplitude one. So over time, every point will be used to denote the bit stream, let's say. Another way to look at it is coherent. If you add the word coherent in everyday use means together. So in this, technically speaking, the transmitter and the receiver, they need to be way more aware of each other, what they're doing. The receiver needs to be quite more intelligent than just looking at incoming power levels. The stricter sense, the stricter origin of the word coherent is coherent phase demodulation. That's what's happening at the receiver. Without going in too much further detail, which could be possible, but I'm not going to too much, there is a couple of keywords, let's say, to be aware of in this arena. So here we have our constellation diagram again. So zeros and ones denoted by points in that constellation. We have something called baud, or symbol rate, which is how often the laser actually does give a light signal. But then there are the other properties that we've seen. So phase and polarity that make up the eventual data rate of this signal that we're transmitting across the fiber. Data rate and then plus some overhead for forward error correction schemes, which actually do make up a significant part of this story. At the end of the day, there's a very important metric called spectral efficiency, which is the ratio of how much data we are transmitting by usage of so much spectrum in the optical fiber that we are using. So how does this look from a product development point of view, very high level? So these technologies don't come easily as a piece of bread in the supermarket. They take time to develop, to design and test and develop, let's say. So typically every 4 years there is a new iteration, a new generation, if you will, of that coherent technology that's introduced. Starting out in 2009, And at the moment, we're at 2024. Well, we have the WaveLogic 6, so the 6th generation of coherent modem technology over there. What does this graph show? 100, 200, 400, 800. What does this mean? So this is the maximum data rate per wavelength supported by the modem technology. So if in 2017 we issued a modem technology for up to 400 gig per single wavelength, that has now increased by a factor of 4. So we have a single modem, single wavelength technology providing up to 1.6 terabit per wavelength. And of course, that's up to, so this is all variable, right? If there's lots of noise or if it's a very long path in your fiber optic network, you might not be able to reach such extremely high data rates, but then you just downgrade, you do whatever you can. And another aspect of this diagram, you see here this larger, for the people in behind, it might be difficult to see, but these are, let's say, integrated modems, so transponder form factor solutions. But here you see, for those that can recognize it, a QSF PDD, so a pluggable. So as of the 5th generation, we decided, look, it doesn't make sense to develop one solution. Let's make two. Let's bifurcate the development path and introduce two streams of solutions, a form factor optimized, energy optimized, and a performance optimized that does go up to 1.6 tera, and a form factor optimized or energy optimized for up to 800 in the latest edition. So aside from that, this is proving to be a very successful approach, this coherent technology, right? There is another graph that goes a little bit strange. It goes downwards, but this is the reduction in power usage per bit, in fact. So there is a clear plus side in minimizing, let's say, the number of lasers, to put it very bluntly, right? For the same amount of capacity, there is just less and less equipment required, so less and less power. How does this look? How does this map out, let's say, in terms of solutions? Well, very sketchy, but one has to do something. Again, we have the whole spectrum of the fiber optic WAN outlined over here. Access, metro being 100 kilometers or something thereabouts. Multi-span metro or regional, long haul up to including submarine, tens of thousands of kilometers. So typically we see that the more one gets to the edge, the pluggable form factor is the way to go. It works just best. It's the best fit. Moving over to longer distances, typically there's larger capacity requirements over there as well between the same endpoints. And there we go for the integrated modem form factor. So that's transponders, typically as large as a laptop, maybe for the largest ones. So some examples of I promised activity in the region, so I'll show 3 examples of recent activity that we did, just to give you a flavor of what's happening here. So here's the first example. So what did we do with this particular customer, this particular Ciena customer? So we worked and we looked at a set of paths in the fiber optic network of this particular customer. We deployed the latest, so the 6th generation of coherent modem technology at 2 endpoints. So the darker red path between Oslo and Trondheim, 650 kilometers. So it's this particular arrow. So 650 kilometers. meaning that there is lots of photonics. There's repeaters, or better known as amplifiers. There's other ROADM sites in there, so photonic switches where you can tap off a wavelength, if you will, along the way. So that 650 kilometers, we were able to indeed push the maximum of the 1.6 tera out of those boxes. Slightly longer path, well, slightly, no, it's twice as long. It's 1400 kilometers in the orange. 18 spans, so again, that means like that there is 18 times, there is or 17 to be exact, there is an amplifier en route to amplify again the signal because the fiber attenuates the signal. This time from Oslo to Bergen, indicated with the yellow arrow. More than twice, but yet again, we did manage to push out 1.4 terabit per carrier. How does this look like? So here we have spectrum, and here we have the carrier indicated. So this is the single wavelength, let's say, in both cases. So this is, in this particular case, you can see there's not much other wavelengths running about. There's just one indicated over here. And here we see a carrier, a 200 gigabaud carrier. So 225 gigahertz of spectrum. And that constitutes that single wavelength. Another example, with another customer, we deployed the fifth generation. This is a couple of years back. So we deployed the fifth generation, which is an up to 95 gigabaud and up to 800 gig per wavelength technology. And we deployed that across, again, a part of the terrestrial network of that particular customer, which runs between Amsterdam and Copenhagen, 1100 kilometers. So again, there's lots of ROADMs and photonics in between. And yeah, we were able again to push up to the highest attainable data rate for that particular distance. For 1100 kilometers, we were able to push it to what it can do. And again, what could that mean? Yeah, well, 800 gig data rate in a single wavelength, so 4 times a 400 gig. Third example. So here we deployed the Coherent pluggable form factor. So we deployed Ciena plugs in a third-party router across a third-party WDM line system. And again, 900 kilometers and 1300 kilometers. So again, lots of amplifiers and ROADMs in between. 1 QSFP at the A and 1 QSFP at the B point between Copenhagen and Stockholm. If you can recall, the 5th generation of Coherent pluggables went up to 400 gig per carrier at best. And that was a success for 906 kilometers and for the 1300 kilometers as well. So these examples to give you a flavor of what this technology can do, with an immediate comment that these are hero experiments. What is a hero experiment? It means not much margin left. So it might not be commercially, let's say, very safe to deploy, but it's at least a technical indication of what can be done. For those of you interested, so ZR Plus was the line interface that we deployed for the 906 kilometer path. And we also deployed a Ciena proprietary modulation of the wavelength. We always follow standards, but being such an R&D intensive company, we like to tinker and think things through and develop stuff ourselves. So we have our proprietary modulation modes as well. So this particular one being called Packet Max 70, so that's a 70 gigabaud carrier. which one, in fact, was needed for the 1300 kilometer path, right? 70 gigabaud is, yeah, it does give a little bit more leeway than 400 ZR plus for those of you who are, let's say, slightly into this field. I should mention, by the way, that stepping back one slide, that we issued a press release yesterday. So I was just not in time to capture it in this slide pack, but we issued a press release yesterday together with this particular same customer for a feat that we jointly achieved across the repeated subsea cable from Stavanger to Newcastle. So there we deployed 1.6 tera across 700 kilometers. So final comment is that these coherent technologies, they are not, let's say, they don't exist in isolation, especially in that case where we deploy them in interop, in third-party routers, sorry, across a third-party line system. So we strive to have our NMS, or domain controller rather, work in such a way across such a multi-vendor environment that the overall end-to-end connectivity model is in fact visible, right? So we strive to that type of situation. Not saying that that is very easy. As you can imagine, there's lots of combinations, especially when, especially between router vendors, it does vary a lot. If the router will accept yes or no that third-party plug, what's doing there, I don't like it, things like this. Like mentioned, Ciena always follows standards, which is the best way to guarantee interop. Other vendors are more difficult to persuade, but we find that some of them are getting there. So such a view from your NMS is the target, let's say, for in these types of interop situations. So we follow standards. One particular one to mention is CMIS. So CMIS compliancy. If you're venturing into this scenario, plugs in third-party routers, remember this particular abbreviation, CMIS. It will help you along the way. I'll skip that slide. So I've given the shortest of introductions into coherent technology and what it can do, and especially, I hope, in this beautiful region of yours. Thank you.